Hawking radiation is the theoretical thermal blackbody radiation released outside a black hole's event horizon. However, just because radiation is observed outside the horizon, it does not mean that it is coming from a black hole. Although it may appear to an observer on the ground that the Sun revolves around the Earth, in reality, the Earth moves around the Sun. Even if a black hole appears to emit something outside of its event horizon, it may only appear that way. For example, suppose that electrons and positrons were created very close to the event horizon due to quantum fluctuations. To a distant observer, particles appear to be emitted from the black hole's horizon when one is sucked into the black hole and the other escapes. We can say, what the observer sees and what actually happens are different. The emission observed by the observer is not caused by the black hole, but by the space around the black hole. In reality, the space around the black hole is losing particles to the black hole and its surroundings. And the surrounding space outside the black hole is also deprived of energy equivalent to the deprived particles. In other words, a black hole can deprive energy in the form of particles even from empty space. And a problem arises in the space where energy is taken away. The space close to the black hole loses as much energy as the lost particles. According to the laws of thermodynamics, heat moves from a more distant space to a space near the horizon. The space from which heat has been lost continues the process of losing heat from the space next to it. Ultimately, black holes steal energy even from empty spaces around them that seem to have nothing to absorb. Let's assume points A, B, and C, respectively, depending on the distance from the black hole. Pair production occurs at A, very close to the black hole's event horizon. Due to pair production, the space loses as much energy as two particles. And two particles are created. Since the space A is very close to the black hole, assume that one of the two particles enters the black hole and one escapes. Even if the energy levels of the two spaces were the same at first, after this phenomenon, the energy of the space A becomes two particles smaller than the energy of the space B. According to the second law of thermodynamics, heat, energy, moves from the space B to the space A. As this process continues, the energy level of each space decreases as it gets closer to the black hole. In the end, a chain reaction occurs in which space closer to the black hole draws energy from space further away. In the end, if you make predictions based solely on things that can be observed from the outside, you may fall into the same mistake as claiming the heliocentric theory based on observation alone. In reality, the black hole does not radiate anything, but radiation occurs in the surrounding space. And ultimately, black holes can absorb energy not only from observable matter but also from the void. This action of black holes may have cooled the universe faster than generally expected. If there is nothing and the conditions are the same, the heat radiation will look like this because it will cool at a constant rate. Let's put a black hole here. The closer the space is to the black hole, the more energy is lost, so the form of heat radiation is roughly like this. Zooming in, let's look at an area with some black holes. Zoom in further to see a region with many black holes. The universe may be younger than expected.